Okay, so we start. I recall the definition. So G is a Lie algebra. G is a Lie algebra. And we define the associative algebra, universal unavailable, as follows. We take the tensor algebra of G as a vector space and take the quotient with respect to these relations. And I assume that by definition, this is the bracket in G. And this is equivalent, at least in the case G is finite dimensional. So assume, for instance, G is, assume the dimension is finite. Then equivalently, we can take any basis. And then the same definition looks as follows. Then UG is the same as taking the free associative algebra with these generators and quotient modulo the relations of this kind. And these are the structure constants. Structure constants of a bracket in the Lie algebra. So this is the same. And even if our algebra has infinite dimension, we can do the same. Just take a basis, which always exists in purely algebraic sense, and do the same. And the result, which I want to discuss now, is the Poincaré-Birkhoff-Witt theorem. Poincaré-Birkhoff-Witt theorem, which says the follows. Let me state it first in terms of our fixed basis. Terms of a basis. And later on, I will give an invariant definition without any basis. In terms of a basis is as follows. Take ordered monomials. Consider ordered monomials with respect to our basis. That is, we have the first vector, maybe in some power, which can be equal to 0, for instance. The next, and so on. So these are ordered monomials, and we claim that these monomials form a basis in our algebra. It's possible that n, if n equal to 0, then we assume that the monomial is 1 by convention. So this is the claim. And it splits into two parts. One part is trivial, and the other part is not trivial. What is trivial? The trivial part is that these monomials span the whole whole space. This is trivial. Why? Because if I'm in principle, the span of arbitrary monomials gives us the algebra. This is evident because our basis elements are generators by the very definition. These are the generators. So if our monomial is not ordered, then you can interchange some letters using these relations. For instance, if you have something like this, we have some x2, x1, we can rewrite it as x1, next x2, and plus something which has lower degree. And by recurrence, we can represent any monomial as a linear combination of ordered. So this part is, I think, is trivial. What is non-trivial? Non-trivial is they are linearly dependent. This is non-trivial. And now I would like to prove this. But my idea is to present a proof in a particular case. So I consider proof, particular case of, I assume G is the general linear algebra. I don't want to write the field. It can be C, any field of characteristic 0. In fact, the theorem holds true for any field without any assumption, but I will give a simplified version. I will write C, but it can be any field. And the basis, and the particular basis, the basis is the most natural one, that of matrix units. Matrix units EIJ. So where are the dimension is equal to n squared, and any order impose any linear order on the by indices ij. For example, if n is equal to, when we have these matrix units, and we can assume for simplicity, for instance, for definiteness, that we have this order on the by indices. Sorry. What I wrote. Oh, excuse me. I would like to write. I'm in this picture. This first, next. So for simplicity, we can assume, for definiteness, we can assume that we impose this order, but actually we can take any other order as well. And I will denote notation. Let me adopt the notation by capital A or maybe B. This will denote any ordered sequence by indices. I mean that A is something like this, which is less or equal with respect to my order, and so on till some ik, jk. So this is, I will call it the multi-index. Multi-index. It serves to parameterize our ordered monomials. Is it clear, or maybe some questions? No questions. Okay. And B will means similar, something similar. And my notation is also K. I denote the length of. For instance, example, for instance, in our case of 2 by 2, matrices A can be something like this. 1, 1 repeated sometimes. 1, 2, 1, 2 repeated sometimes. 2, 1, 2, 1, 2, 2, and K is the sum of all these quantities. So with some example. So the claim I want to prove, claim, and let's denote by E sub A the product, the monomial, the ordered monomial corresponding to some A, some capital A. So this is using this notation. This is some element of our enveloping algebra. So this is the definition. And the claim is that these elements are linearly independent. So this is the claim which implies the Poincaré-Birkhoff-Witt theorem in this particular case of GLM. So I want to prove now it. The idea is as follows. We want to use some special representation here. Use a representation of G on a space V. And I repeat that a representation of a Lie algebra on a vector space is exactly the same as a representation of the universal enveloping algebra. By the very definition, these are the same objects. So this is the same as a representation of, I'm sorry, this is not abstract, by G.L.N. on the same space. So what is V? By my definition, V, I take V by definition, the space of polynomials in n squared variables, which I will denote as xij. Here again, the indices are in this range. So to define this representation, it's sufficient to indicate what are the images of our generators. So by the very definition, this is some T is the notation for my representation. So I have to specify what is this. This should be some differential operators, actually, and it is defined by this formula. Alpha ranges from 1 to n, x alpha I, d alpha j. This is an operator on V, and by definition, d alpha j is the derivative, a partial derivative. So this is a first order differential operator which acts on the space of polynomials, and because the coefficients here, coefficients are also polynomials, it preserves the space of polynomials. And hence, we obtain a representation of the whole universal enveloping algebra. So my idea is to show that the images of our monomials are linearly independent as operators on this vector space. And how to do this? One more notation. I will write symbolically X as the collection of these variables are as ranges as before. And one can say that these, one can view these as coordinates on our space of dimension n squared. And our space V is a space of polynomials on these vector spaces. But I need also another system of coordinates, which is another system of coordinates y, which is related to these variables in a very simple way. Namely, I assume that x is equal to 1 plus y. But more precisely, this means that XRS, I represent it as a delta Kronecker symbol plus RS. If you regard this collection of variables, I'm sorry. If you regard this collection as a matrix with these variables as entries of this matrix, this makes sense. We just represent the matrix X as 1 plus y. Okay? And assume now that we have some B, another multi-index is something like this. an object as before. Some weakly increasing sequence of by indices with respect to our order. And when I want to assign to this multi-index, we assign to B a monomial, but in the variables y's. So I write symbolically, I write it as this product. And it's obvious that these are these monomials in the y letters is another basis. Another basis in our space. So this is just an affine transformation. Instead of taking the origin at the 0, we take the origin at 1, at the identity matrix. And now I want to state the key lemma. The key lemma, which says the following. So assume A, B are two multi-indices as above. And assume that the length of A is less or equal to the length of B. What I want to take, I take the differential operator, which corresponds to our initial ordered monomials, and I apply it to another polynomial, but which is a monomial in terms of the y coordinates, and I evaluate the result at y equal to 0, meaning that all variables are set to 0. And what we get? The claim is that we get 0 if A is distinct from B. And if A is equal to B, we get some constant, which is non-zero. So this is the claim. This is the claim. Now the proof of the lemma. I will give the proof of the lemma, and next I will show that it easily implies our claim. How to prove it? So let's write down exactly what is these operators. By the very definition, we get the following. So I write it, T of A. It is a monomial. It is a monomial of first order differential operators, which is written as follows. The multi-index alpha, which is the sequence, and each alpha range from 1 to capital N. And next we have 1 coefficients, 1 derivatives, 1 coefficients, I'm sorry, one derivatives. It's wrong, I'm sorry. And so on till the end. Till the end. So the summation is over the Greek indices. So this is by the very definition. But let's rewrite it. Rewrite it as follows. The sum of these quantities, the coefficients first, plus something, the rest terms of lower degree with respect to differentiations of lower degree with respect to differential, or in principle is the same as saying that they are lower degree with the total degree with respect to coefficients and differentiation. This is the same. So lower degree terms. And next, what next? Next, we rewrite again, but in the y coordinates. So this will be something like this. No, sorry. And next, the derivatives, but derivatives with respect to x's or y's are the same. So I will make no difference. So this is exactly the same. Or maybe I can write for, okay, to be more precise. Plus lower degree terms. And next, what is this? What is this? I rewrite next that this is first take into consideration only the terms which comes from these Kronecker deltas. And this gives us exactly the no summation here. Plus what we get next. Some terms which are of lower degree and or contains no, not contains, maybe it's better to say. The characteristic feature of these rest terms is that coefficients have no constant terms. So coefficients are some monomials of degree strictly greater than 0, some monomials, not constants. Is it clear? Because what comes from these lower degree terms is written here. But we also have some terms which comes from these. And these are terms with coefficients which contain no constant terms, which vanish at 0. What is important? These terms vanish at 0. And this implies the following. So now apply this expression to the monomial this one, and use the fact that the number of derivatives in A is less or equal than the number, the degree of our monomial. So when we apply these rest terms and specialize at 0, we get 0. This is the contribution. So what I want to say, first, the contribution of all rest terms to this expression is 0. Is it clear? Because if the length of, if the degree here is strictly less, then there are some remaining monomials, some remaining letters wise, which vanish at 0. And if not, there are some coefficients in front, which comes from these terms, which also produce vanishing. So what remains? What remains is just this one. Applications of these derivatives symbolically, I can write it something like this one. Maybe symbolically. A applied to this equal to 0. And because, and here again, if the length is strictly less, then the result is 0. And if not, this is the critical case. But this can be equal to 0 or some constant. The constant comes from something like this. If you have something like in some power, and we apply this to exactly this monomial, so we get n factorial. So, okay. So this is why I need the assumption that the characteristic is 0, because in characteristic P, in principle, such a constant could be 0. So this is essential here that our field is characteristic 0. So this is the lemma. The lemma, it's the end of proof of the lemma. End of proof of the lemma. Maybe any questions? Is it clear? Okay.
It's clear, but looks like magic.
Looks like what?
Magic, some strange representation.
Okay, I will explain later why it's a natural proof and not tricky. It looks maybe tricky, but it is not. I will explain why it is. Thank you for this remark, it's important. And now end of the proof. End of proof of Poincaré-Birgov-Witt. So we assume that we have, that we have some linear relation. Some finite linear combination which is equal to 0. And I want to prove that all coefficients are 0. How to do this? So let's case is, I assume that all coefficients here are non-zero. And I want to conclude that that actually this linear combination is empty. This is the same. So let's assume that K is equal to the maximal value of all lengths. Okay. Now, so apply the lemma. By taking to the monomial B, where B is equal to K. So we apply, so more precisely, we consider, take this T, apply to this monomial and take y is equal to 0. And what we get from the lemma, we get that the coefficient CB is equal to 0. And this can be, this holds for any B of this length, K. So we get that actually the top degree coefficients are all equal to 0. So this only may happen if actually our linear combination is empty. So this is that. So this is that. Is it clear? No question? Okay, so this is the end of the result. And now some example. I remember when I was a freshman, I could not understand why to prove this Poincaré-Birgit theorem. It seems to be obvious. Why is it possible that the ordered monomials are not linear independent? But here is some example, which shows that there is something non-trivial here. So some example. Why Poincaré-Birgit is not trivial. The example is as follows. So assume that we have an algebra, take an algebra, which is obtained in the similar way. So A maybe, it's a bad notation. So calligraphic A is obtained as follows. We take the algebra with 3 generators, say X, Y, and Z, and subject to 2 relations. XY is equal to X. XZ is equal to X. And YZ is equal to Y. So this resembles the Lie algebra commutation, some Lie algebra, these are the brackets, but what is similar? The similar is that the commutator, so I mean expression sum xy minus x is a linear combination. Linear combination. I mean this commutator, which is a 2-degree expression, is actually equal to something which is of degree 1. So this is just as in the case of Lie algebra, but only this is not Lie algebra, because this prescription does not give us a Lie algebra. The Jacobi identity is not satisfied in this case, but in other respects, it looks as it would be some three-dimensional Lie algebra. But the claim that Poincaré-Berghoff-Witt fails in this case. So one can take ordered monomials, for instance, ordered monomials, any order, for instance, this one, y, are not linearly independent. So this is an exercise. I will give it as an exercise, as a homework. This is a good exercise which shows that something does not happen. Now some comments.
I'm sorry.
Okay.
Does this mean that we are not able to introduce an order on these monomials?
I don't understand.
So we mostly used an order on monomials.
I think the question here is which part of the proof fails in this case?
The monomials are dependent. Monomials are dependent. Okay, the secret actually I make, okay, let me, a little secret.
Oh, okay, I see.
More is true, more is true, more is true. Actually, these relations imply that x is equal to 0. It is not obvious, but it can be deduced from this. These are bad relations. They are linear. They formally are of the form. Formally, we have something like this. The relations are of the form with some constants. But the constants are bad. The structure constants are bad in the sense that the Jacobi identity fails in this situation. Then in this case, it may happen that the Poincaré-Berghoff-Witt fails. And this is just an example of this situation. Okay, is it? Maybe some.
Yes, it's clear. Yes, thank you.
Okay. So what next? So one claims some comments. To Poincaré-Berghoff. First, I promised to give another formulation without basis. This formulation is as follows. Let's take the symmetric algebra. The symmetric algebra of vector space G, which is the same as this is polynomials on the dual space if the dimension is finite. But irrespective to this condition, the symmetric algebra is something which is defined always. Okay, and remark that U of G, our untitled algebra, is a filtered algebra. Filtered algebra. I call that we need to define what is a filtration. So by definition, the nth term is the span of products of Lie algebra elements. Lie algebra elements, monomials of degree. The length of the product should be less or equal to it. So this is a filtration. This is a filtration. And Poincaré-Berghoff-Witt just says, and this filtration is compatible, is consistent with multiplication. So this is not only the filtration of a vector space, but it is a filtration of an algebra. Poincaré-Berghoff-Witt exactly says that the associated graded algebra is the same as the commutative symmetric algebra. So again, what we have here? You have here the fact that we have a natural map from this to this object. Okay, so what this means? What is this map? If you have some homogeneous element, say homogeneous and x1 and G. So we take the same product in this vector space, and but modulo and what we get is we get exactly this map by the very definition of associated graded algebra. So we have this map. So again, what is trivial? Trivial is that this homomorphism is onto, it's surjective. I think this should be evident. By the same reason, because the Lie algebra elements generate the whole universal enveloping algebra. Is it clear? Maybe some questions. And again, why it is a algebra homomorphism? Again, the idea is that the top degree term, if you take top degree term with respect to the filtration, then the product in the universal enveloping algebra becomes commutative, modulo lower degree terms. And why this happens? This happens from the very definition. In the simplest case, we have that xy is equal to yx modulo linear term, which is this one. And by induction, we see that the same happens in general. If you take some two elements and their product is commutative modulo lower degree terms. And this exactly means that the graded algebra associated to our universal envelope algebra should be commutative, and it is graded. And it is actually the same as the symmetric algebra. So what is trivial? The trivial is that this map is onto. What is non-trivial? Non-trivial is that the kernel is 0. So this map is injective, and hence it is isomorphism of commutative, of graded commutative algebra. And this is exactly Poincaré-Berghoff-Witt. Exactly. So this is some invariant formulation of a Poincaré-Berghoff-Witt, which says, I repeat, that the graded algebra coincides with the symmetric algebra. And the next remark to my proof. The next remark is that by virtue of Adot theorem, which says that any finite dimensional Lie algebra is contained in some GLN for n large enough, it implies that Poincaré-Berghoff-Witt holds for any G of finite dimension and the characteristic 0, because my proof holds only in this case. There are any other proofs. There are other proofs. But they are intricate. I think my proof is, it is not in full generality, but it is simple. Our proofs can be found in the Bourbaki, Lie groups, Lie algebras, chapter 1, the Humphrey, the book of Humphrey about Lie algebra and their representations, the old book by Jacobson, Lie algebras, and probably, but there is also quite a different proof. The so-called diamond lemma, very general fact. Bergman, a paper by Bergman, not a book, but a paper. I highly recommend you this very important paper. In Advances in Mathematics, it is in open access because Elsevier open accesses for after 3 years, so it's open access. A very general approach to Poincaré-Berghoff type theorems, not only for Lie algebra case, but which works in our situation as well. And now I would like to explain the origin of my proof. To explain it, I need to assume that you know what are Lie groups. In principle, I will not use in my course, I will not use Lie groups, but assuming that we know something about Lie groups, I can explain the origin of my proof. So assume the base field for simplicity. The base field is R. G is a Lie algebra, the Lie algebra of some Lie group. And the idea is follows, more generally. So assume that M is a smooth manifold. M is a smooth manifold. And I want to consider differential operators. And differential operators on M are can be viewed as sections, as global sections, global sections of a bundle, over M. In general, so assume that, say, more precisely, differential operators on M of order less or equal to n. I mean that differential operators with at most n derivatives are sections of a certain finite dimensional bundle. How to write it? Say some D M C, some bundle. What does this mean? We take some chart, and we have some coordinates, some coordinates. In these coordinate systems, we can write as usual a differential operators with some expression involving coefficients, smooth coefficients and derivatives, and we take this object at a given point. And this is a fiber of our bundle. And if we take another coordinate systems, there is some transformation of some rearrangement of these derivatives and coefficients, some transformation. And this just means that our differential operator is a section of a certain bundle. Okay, so this is this. And now we can imagine that this n can vary. So we get actually a sequence of bundles. We get as n varies. So we want to consider an arbitrary differential operator of arbitrary order. So we get some sequence of bundles, some nested sequence of bundles. And so on. So we get some filtered object, and we can take graded object. We can take the bundle, the quotient bundle. What does this mean? We consider differential operator of order at most n modulo differential operators of smaller order. And what this means? And this is actually the same as what can be called the symbols of differential operators. And this is again some bundle, but what is this bundle? And we have to take the tangent bundle and its symmetric power of degree n. Okay. So I repeat again. So taking differential operator of some fixed or some order less or equal to n modulo smaller degree operators, we get these are sections of a bundle, and this bundle is nothing else as this nth symmetric power of the tangent bundle. Okay. So now assume that take M as our Lie group and take left invariant differential operators, say, of degree, and apply this construction to left invariant differential operator. And in this case, for invariant differential operators, such operators, because our group acts transitively on itself, any invariant operators is uniquely determined by its value at any given point. Such operators are uniquely determined by values at any given point, and say at the unity of our group. But what is this? But when we get the symmetric and this is exactly the n-symmetric power of the Lie algebra. So what I want to say? I want to say that taking the symbols of differential operators, you get exactly the object of the type we want, namely symmetric, which lives in the symmetric algebra. So the idea is just to prove that that what we get has the same size. So what informally is the meaning of Poincaré-Berghoff-Witt? It says that the size of a universal enveloping algebra is exactly the same as the size of a symmetric algebra. Now, the idea how to relate this to universal enveloping algebra. The idea is the universal enveloping algebra acts by left invariant differential operators. We realize it. At least we have some map from universal enveloping algebra to left invariant differential operator. What is this map? We start from degree 1. We take some Lie algebra element and we realize them as left invariant vector fields. And here my claim is obvious. The left invariant vector field is uniquely determined by its value at any given point because of the transitivity of the action. So we take the algebra element is exactly the vector in the tangent space to the unity. Okay. And more generally, any element of universal enveloping algebra can be represented as a sum of products of Lie algebra elements. So we have a product of vector fields, which are viewed as first order differential operator, and such a product is also a differential operator, but only of some arbitrary degree, which is equal to the length of the product of the Lie algebra. Okay? So we get this map, and my proof is essentially this argument, because I can, my proof is it exactly follows this construction, but here I take as G, I take the GLN, real or complex, actually it's the same, does not matter. And this explains this passage from X to Y. What this means? This one is exactly the unity of the group. And why I need it just to take a coordinate system around this element. So this is the simplest way to introduce a coordinate system in this group G line. In general, this is some curved space, but locally, there is no difference between this curved space, a manifold, and the affine space, the space of matrices. Okay? So the idea is, and our elements, the elements what I wrote, I mean this first order element, which comes from this, is exactly the vector field. This is exactly the vector field, which is used as a first order differential operator, the first order differential operator, which is left invariant, So what I want to say, I take X, which is a group element, okay? And I introduce near to the identity, I write this G as 1, maybe it's better to write it as smooth. As G varies and we differentiate with respect to Y, we get a first order and left invariant differential operators. And this expression just comes from this picture with G equal to X. So this explains, I believe, the origin of my argument. Maybe some questions about this? What next? Now I would like to return to my picture. So we have this idea. This is the same. And informally, Poincaré-Bergoff says us that the size of this non-commutative algebra is the same as that of this commutative algebra. But we want something more, because these two objects are of the same size, at least as vector spaces. We want to not only to establish this equality, but we want to establish some equality of this space directly, without this passage to taking the quotient, which is implicit in this notation. So what we want? We want to find some linear map. So maybe the title of my subject is the symmetrization map.
I'm sorry. Do you need a G star on the left or
G star?
Yes.
Why? No, I don't need this. And to explain why I don't need. So assume G is abelian, which means that the bracket is identically equal to 0. Okay, so what is U of G? Then U of G is exactly the tensor algebra modulo the relation but this is exactly the definition of a symmetric algebra. The symmetric algebra is the algebra of polynomials on the dual space.
Ah, I see. Okay.
So
Okay, thank you.
this is some subtle point here, subtle point. The idea, it's important. So let me repeat this. If you take a basis, if is a basis G, then we can treat this basis, we can treat each xi as a polynomial on the dual space. Okay? And so any polynomial expression.
Yes, that's what I thought. Yes.
Okay.
So by S of G, you mean the tensor or the factor algebra of full.
Exactly.
Mhm. Okay.
Exactly. This is the standard definition of a symmetric algebra of a vector space. This is linear algebra. This is.
I thought that by symmetric algebra you mean like polynomial functions. So
yes, they are polynomials functions on the dual
space. Okay.
On the
okay,
dual.
thank you.
I just tried to explain. This is a right question. This is a right question, but it refers to linear algebra. There is no Lie algebra, no Lie groups. This is linear algebra. This is linear. Okay. Okay. So what I want? So symmetrization map. I want. The title is symmetrization map. So I want to identify as vector space, I want to construct a map from the symmetric algebra to the universal enveloping algebra directly, without any graded object related to a filtration. And what I want a map such that informally, it holds that this is the identity map. So what this means? If you take some element here, some monomials, okay, we take its image here and take its top degree terms with respect to our filtration. So actually we pass to the quotient space. And I want that this result should be the identical map, the identity map. The definition now is as follows. The definition. So I need a notation. So write multiplication in enveloping algebra is in general non-commutative using this symbol. So something like this. This means multiplication in a non-commutative universal enveloping algebra. So this is just a convention, just to distinguish it from the commutative multiplication in the symmetric algebra. And now the definition is as follows. It suffices to define the image of homogeneous element. So for homogeneous in the symmetric algebra, I want to define its image in the universal enveloping algebra as follows. I have to do something with these commuting letters, but I want to convert this product in some object in a non-commutative algebra. How to do this? In this formulation, it seems that the most natural way to do this is just to put as follows. Take the summation over all permutations. This is a bad notation. You need some notation for the symmetric group. I will use the Gothic letters. So this is the symmetric group of the group of permutations, and takes such an object. This is what is called symmetrization. So, for instance, you have two letters. We have example. If you have this object, you take the half sum. Why we adopt this definition? The idea is the right-hand side should be independent on the order on the left-hand side, because this is the same as this one. So the result on the right-hand side should be the same. It should be invariant under any permutation. And how to resolve this? The most natural idea is to take any possible permutations and then average over all these permutations. Okay. So what is clear here? It's clear from the very definition that the right-hand side is independent, this map is defined correctly. It does not depend on the order, because this object does not depend on the order of its letters. Okay? And it is a degree preserving map, because the degree here is n, and here is at least less or equal to n formally. But we also have this property. We have where I wrote it. We have this property. Why? Because the top degree term of this expression. So what means, I repeat, top degree term? We regard this expression modular lower degree terms. And it exactly this one. This is something lying in a commutative object. This is commutative object. And the top degree term is the same, because we have n factorial terms and we divide by this factor. So this holds true. Why it's remarkable? This is remarkable for the following observation. We have I recall that I have introduced the adjoint representation. The adjoint representation. Sometimes one calls it adjoint action. Of the Lie algebra. G on itself. Namely, the operators. Corresponding to a given element G is which means that if you want to apply these operators, this is operators on this space, applying this operator to some y, we get the bracket of these two. And I recall that the Jacobi identity exactly means Jacobi identity exactly means that what is a Lie algebra morphism, hence a representation from G to end G with, this is an associative algebra, which is viewed as a Lie algebra with respect to a bracket. Okay, so this means that it is a representation on this space G. The Lie algebra acts on itself by taking this bracket. And the claim, the symmetrization map is consistent with the adjoint action. What this means? Look at this picture in this object. I claim that we have natural action. We have natural actions of G on this commutative algebra and on this algebra. What is the action? What is the action here? Okay, we have an action of Lie algebra on itself, but it extends uniquely to an action of a symmetric algebra. What is the idea? How to extend it? So what we want to define? We want to define the action of some product. How to do this? The extension goes by applying the Leibniz rule. This is the sum. We apply to this and take the rest. And what is, I use the same symbol. What is, if we apply here, exactly the same, with multiplication understood in the sense of the non-commutative algebra, which also coincides with this. But what is this? This is taking commutator in the non-commutative algebra, because this is exactly as, this is the same. And again, we can apply the Leibniz rule in the non-commutative algebra context here. So we have a representation here and a representation here. And the claim is our map, the symmetrization, is equivariant with this action. And why it's holds true? I have to finish already. It's trivial. It's trivial because in both cases, we apply the Leibniz rule. This is the first observation. And the second observation is that we taking this averaging and taking Leibniz rule, these two operations interact very well. They can be interchanged. We can first take averaging and then apply the Leibniz rule, or vice versa. And because of this, the symmetrization map is indeed equivariant. So what is trivial and what is non-trivial? This seems to be evident, but something is non-trivial. The only actually non-trivial piece of his story is that this definition is correct because the right-hand set does not depend on the order in this product. This is the only point which is important here. So I want to finish at this point. So my claim is that the symmetrization map is not only an isomorphism of vector spaces, it also has an important property that it commutes with the natural representations, actions of a Lie algebra on. And my final remark, if we know the Lie group context, and if we know that our Lie algebra is the Lie algebra of a certain connected Lie group, it is represented in the real field case, it's always the case. In the case of finite dimension, we always can view finite dimensional real Lie algebra as something corresponding to a connected Lie group. Then the Lie group operates on this object and on this object in a very natural way. For instance, in the case of GLN, the Lie group is the group of non-singular matrices. It operates by conjugation. And this operation, the symmetrization, is equivariant with respect to this action by conjugation. And this is especially evident. If you look at this formula, it is equivariant with respect to conjugation. So I would like to just do equivariant with respect to conjugations, which is X is transformed by this way with some matrix G. So at this moment, I would like to stop. Maybe I will switch off the recording, and if there are, oh no, sorry.